let's go over PID control. So PID control is a form of control that you'll see be used in different forms of engineering and robotics. And so let's get on with that. So first thing we need to know is what is error. So error is the difference between a target value and a current measured value. So as a function over time, error is e of t. So that's the error at time t. Is going to be sp minus mv of t, where sp is the set point or target, and mv of t is the measured value at time t. This measured value comes from a plant, which is just a term for the system that we're trying to control. In the case of robotics, that plant would be either the entire robot itself, a mechanism on the robot, or a motor. In order to use this error to control a plant, then we need to make use of something called feedback. So feedback is going to be the term for a type of loop, so a feedback loop. So a feedback loop takes an input, performs some mutation on the input, in this case it's going to be the controller, and then feeds that output back to the original input, which is going to be through some process. And once it's processed, it produces the output, which then gets fed back into the controller as the input. And this continues as a loop on and on and on. So now let's talk about proportion term. So imagine you want to move the hand of a clock to a certain position. So say that I want to move this is the clock hand, and I want to move it from here to the 12 o'clock. Right? So I start off by pushing it, and then what happens is I push it far past the goal point, like that. So to fix it, you push it back the other way, but with a bit less force than last time. And then you keep doing that until you reach the goal. And this is an example of proportional control. So proportional control, or the proportion term, or p term in PID control, is the direct ratio of the error function. So you're going to have a function p of t, which is going to be the proportion term at time t. It's going to be kp, which is just some coefficient, times e of t, which is the error. So the coefficient kp is the gain that produces this ratio, and then we feed this output of the proportion term to the system. So another way to think of it is a pendulum swinging side to side and then slowly coming to a stop. That's p term. Derivative term. So the p term, however, produces a lot of oscillations, as we saw before with our clock hand. So we can try to minimize the oscillations by decreasing the speed of the force we apply over time to the clock hand as we near that goal position. As the clock hand gets closer to the goal, we're going to slow down that pushing force. So we're going to start here, and then we're going to push hard and then slow down as we reach it, and then slow down as we reach it. So less oscillation. If our focus on proportion control in an example is position, then the derivative term is going to focus on the velocity or the speed, because the derivative of position is speed. And the reason why is because the derivative of math is a change in a function with respect to the change in another function or variable. So with position, the change in position over time is going to be speed or velocity. In this case, the derivative is going to be the change in error with respect to time. So we see our function d of t is going to be kd times the change in error over the change in time. And now we get into the integral term, or the I term. So now we're having issues with missing the target position a little bit, or when we're slowing down. So we might miss it a little bit as we slow down. Right? So to fix this, we just apply a tad bit more force than we normally would as time passes, and then slightly more force. So that's our integral. So the more time that passes, the slightly more force we're going to apply to the clock hand. The integral term in PID control is meant to apply a bit of extra oomph, or a little bit more power, an additional, just some additional force, like we saw with the clock hand, to reach the set position over time. In the case of, and that is a metaphorical reach, right? It doesn't always have to be that you're reaching a position. You could be trying to reach a speed. You could be trying to reach an acceleration. But I digress. An integral in math is a sum of an infinite number of small parts of a function. You can think of it as the area under a curve. So with our integral term, we're going to take the total amount of error over time. So you're going to see that that's going to be our previous total error plus ki, so that's our coefficient, times the change in time times the error at the current time. So then we have our control function. So using these terms together, we can create our control function for PID control, u of t, which is going to be the sum of all three. And there is a link right there to a really good video that I will link later. Here is a Python script that is going to show you how we visualize these terms. So this is with coefficient, so this is Kp is equal to 1, Ki is equal to 0, and Kd is equal to 0. So as you can see, this is the proportion control. So what our goal here is we're controlling a motor that's bearing a load. So what's going to happen here is we're trying to reach 10, right? So that's what we're trying to reach, is 10 meters per second as our speed, right? So we're trying to reach 10 meters per second as a speed, okay? And so our P is going to go up to 10 and then down, and then it's going to keep on doing this again and again and again and again and again. As you can see, there's a lot of oscillation, right? It's not really holding steady. And so the way to fix that, and it's a rather large oscillation. So what we're going to do now is we're going to decrease that amount. And now we do this. You see now the amount of oscillation over time has decreased just a bit, right? So now it's a lot smaller, right? So now you can see that, yes, it's getting closer and closer to that goal. So now, but we still have a lot of oscillation here, right? So we want to minimize that. So we're going to try and minimize that by setting our d term to some value. So this is kd. So now, as you can see, now that we've added kd, we see the green part goes like this, right? And now our oscillation is very small now, right? It's much smaller. But as you can see, we're kind of overshooting and undershooting our position a lot. So to fix that, we're going to add a little bit of I-term into the mix as well. And now, as you can see, everything is holding steady, right? So our P term is now oscillating around 0. Our I term reaches a steady state, and our derivative is controlling the amount of oscillation. And so that is PID.